final presentation of the day is by Mir Mamunuzzaman from the University of Twente, and he's going to be talking about approximation for control of Port-Hamiltonian systems. And so thank you very much for giving the presentation, and away you go.
Yeah, thank you. I put the title of my original project, Approximation for Control of Port-Hamiltonian System. But today I mostly talk about database approximation of irrational transfer function. So I start with an example. So as a test case, I took a vibrating string, which is stationary at one end and free to vibrate at the other end. And we can model such kind of system with the following wave equation. I consider also some internal dampings to introduce dissipation. And we know from a PDE point of view, we need to set right boundary condition. And from system point of view, we need to select right variables as a input. So for such system, I took force as an input at the free end, and I also measured the vertical displacement of the string, which is the output of the system. So by selecting this input and output, we can compute the transfer function for this system. And we see this transfer function is an irrational one. Since most of the practical controller design is based on rational transfer function, that's why we would like to have an approximation of the irrational transfer function by a rational one. So in this work, I am considering a database approximation. So a frequency domain input output data is given. Then I would like to have an approximate model which has a Pseudospectra realization that interpolates our original data. Here I show the frequency response of my irrational transfer function, and the red dot is the frequency point I took as an input and output data. So now I will discuss an important property of many physical system, passivity. For a precise definition, we need store function and supply function. But in a loosely sense, passivity means the inability to generate energy. And this is important in a network of system and also some feedbacks. And this an equivalent property of passivity for transfer function is positive realness. So positive realness can be defined as a rational function which is stable and which maps open right-half plane into a closed right-half plane. Then we can say this transfer function is positive real. So as this is important property, so we would like to have this property in our approximate system. So I will investigate our original irrational transfer function, and we see there are infinite of simple poles and zeros on the imaginary axis. And if we give any positive real value, the transfer function give always positive values. So our system is the transfer function of the system is positive real function. So now we can formulate our problem. So we are given a data set, and we'd like to have a positive real function that interpolates our data, provided that this data is collected from a passive system. So for this database approximation, so the key is the Lowner framework, and the Lowner matrix is the key of this Lowner framework. We can define this Lowner matrix if we are given two set of pairs of data, and in this pair of data there is an underlying function between these two data. Then the divided and difference matrix is called the Lowner matrix. This is important because it encodes all the system's informations, and the rank of this matrix is related with the complexity of the original system. And another importance is when we are considering Lagrange basis for rational interpolation, then this Löwner matrix naturally pop up into the picture. So I will not describe this rational interpolation in details, but I will show you very basic steps of this Löwner framework. So to construct this Löwner matrix, we have to split our given data into two sets. So one set we call left points and right points. And then we construct this Löwner matrix and also shifted Löwner matrix. So if we assume that this data came from a rational transfer function, then shifted Löwner matrix actually the Löwner matrix of the shifted rational function. Then we'll express the realization in a way. In reality, we don't know the complexity of the system a priori. So what we do, we take a lot of data and then we project this data into a subspace by singular value decomposition. And then we'll get this realization. And there is a epsilon, so this should be 0, but due to numerical complexity, we always have some value here. So there is always a trade-off between this accuracy of fit and complexity of the model. So till now I haven't introduced the passivity into Löwner framework. So we can do that by recalling a well-known problem, Neval-Nina peak interpolation problem. And it says that if we have a data set and if we construct a matrix which is called peak matrix, then we can construct a positive real rational function if this matrix is non-negative. Now we have some similarity of this matrix with our original Löwner matrix. So if we are given a data and we take the mirror image of this data with respect of the y-axis or imaginary axis, then our Löwner matrix is exactly the peak matrix. So then we only need to check this matrix condition for the passivity. So I show you what we see by applying this Löwner framework. At first, I was applying for some rational transfer function. So here I plot Bode diagram and Nyquist diagram. So Nyquist diagram is a very good picture to show that whether this transfer function is positive real or not. So if we have the Nyquist plot in the right half plane, then we can say that this transfer function is positive real. So the original one, we see the blue one is on the right half plane. So this is a positive real transfer function. And here we see the green dots is the data we have used to approximate this transfer function. So at the first time we get some unstable approximation. It is very logical because this rational function we don't put any constraint on the poles. So then in the post processing I make this unstable system to stable by mirroring these unstable poles and zeros on the left hand plane, and we have the similar kind of frequency response. But the advantage is we now came up with a positive real transfer function, which was not in unstable case naturally. So we applied the same for our original irrational one, and we see this approximation. It interpolates the data very well. And we also at the first we came up with some unstable models, and by stabilizing this approximation, but we don't came up with positive real transfer function. So for this system, the Nyquist plot is a very messy, so I skip to show that one, but we cannot come up with a positive real for this irrational transfer function. So then we investigate why this kind of instability, or in case of not getting a positive realness, come from. So we already see this Löwner matrix and shifted Löwner matrix encodes the information of the original systems. And when we use this framework for system recovery, then the eigenvalues of this matrix pencil actually emit the pole of the original system. So the sensitivity of these eigenvalues is important to analyze, and this as the sensitivity of this eigenvalue is affected by the location of these interpolation points and how we partitions this data into left and right points. So there is an important comments on what is the difference when we are using this Löwner framework in model order reduction and when we are using for system recovery, but I skip that part. So for this sensitivity, there is a very familiar tool which is used, that is Pseudospectra of the matrix pencil. So this Pseudospectra of a matrix can be defined as the eigenvalues of a perturbed matrix, where perturbation is measured in some norm. And if we apply the singular value decomposition, then we came up with an equivalent definition. The advantage of this definition here is the resolvent of the matrix, which suggests connection with the transfer function. So now we are considering a perturbed system. So here this Pseudospectra is incorporated with this perturbation, which we also can think as a feedback operator. And this perturbation is a structured perturbation, and we also consider the perturbation in system matrix and also the E matrix. So now the problem can be formulated to find a Löwner matrix and shifted Löwner matrix near our computed Löwner matrix, which can be bounded. And the eigenvalues is in the pseudospectra of these newly found Löwner matrices. So there are here we can formulate two problems. One is finding this matrix, and one is having idea about this boundness. So what we are doing currently to have some idea about this boundness, and one of the logical idea to get interpretation with the passivity radius. So the next two slides I was showing what I'm doing now with this passivity radius in finite dimensional setting and infinite dimensional settings. So for finite dimensional settings, if we have a perturbed system, and if we increase the perturbation in some norm, and the minimum norm that makes the system not passive, that is defined as passivity radius. And this passivity can be lost. This passivity we already have defined or related with the positive realness. So if the system becomes unstable, then the passivity is lost. And the second condition is this is actually some spectral zeros. And these spectral zeros should not be purely imaginary. So if any of these condition is fulfilled, then we can say the passivity is lost. The first condition is well studied in the literature, and we can came up with the singular values, maximum singular values of the systems with stability radius. And the second condition, we are considering some linear matrix inequality to get some boundness. Then we try to extend this result for infinite dimensional case. So where we consider the feedback system, where the original transfer function is a positive real one and K is a admissible feedback operator. Then we try to find a minimum feedback so that the positive realness is lost, provided the original transfer function is positive real. And we also formulate two conditions when the passivity is lost, like the finite dimensional case. So that's what